The human brain may sometimes be a very annoying thing. It is designed to constantly reach for the unattainable. Moreover, subconsciously, we're most interested in phenomena we don't understand or those hard to understand. Therefore, millions of people on Earth can worship celebrities without paying attention to other beautiful guys and girls around. We're most attracted to mysterious black holes when it comes to space, mind-exciting objects that are difficult for the human brain to comprehend. Here is where human curiosity comes in, making everyone watch tons of videos about black holes, trying to figure them out. In the next couple of minutes, we will not be repeating ourselves and explaining the black hole's paradoxes and structure. Instead, we're going to talk about their types because they're different. Theoretically, they can also be white. In addition, they may be the key to understanding dark matter, quantum theory, and even Planet X in the solar system. So, dear friends, make yourselves comfy, because the next few minutes will be very exciting. So far, there is no precise classification of black holes. Only 100 years have passed since their existence was theoretically predicted. It's only been 100 years since their existence was theoretically predicted, and only 3 years since the first photograph was taken. At the moment, only a few dozen black holes have been officially confirmed, all while others are just considered candidates and are only calculated mathematically. This math is good and is confirmed 99% of the time. But still, with such scarce data, it would be nonsense to claim that we can make a precise classification. Therefore, many black hole types exist only on paper. In this video, for your convenience, we will explain which of the black holes we mentioned have been confirmed and which remains just a theory. Let's start the breakdown not from black holes, but from white ones. When Karl Schwarzschild solved Einstein's equation of relativity and predicted black holes in 1915, many scientists immediately started thinking about symmetry, because our universe loves balance. For any positively charged particle, there is a negative one. There is an opposing force for any force, and if it has not yet been found, it is because our knowledge of physics is insufficient. Many physicists are even convinced that the universe's total energy is zero. Everything is so balanced. When it comes to black holes, scientists immediately began to look for objects opposite to them. Igor Novikov and Nikolai Kardashev mathematically found them. They even didn't have to go far. Just like Einstein's and Schwarzschild's equations predict black holes, these same equations also predict objects opposite to them. They called them white holes. Their functioning scheme is simple. If a black hole absorbs the matter and even light, then a white hole, on the contrary, throws everything out. If it is impossible to get out of a black hole, it is impossible to get into a white one. In short, everything works utterly opposite, but unlike black holes, it exists only on paper. White holes mathematically can exist and are confirmed by the theory of relativity. Moreover, they can become the key to wormholes that allow you to travel around the universe like in Interstellar. However, not a single attempt to find it was successful. In 2006, Israeli scientists Alan Reder and Shlomo Heller stated that a white hole caused a gamma-ray burst of GRB 060614. They later noted that a white hole also caused the Big Bang with which our universe began, but there's never been any real proof. Now, most scientists believe that white holes don't exist. However, remember that all the stars, planets, and galaxies are only 4% of the universe. The other 96 with the dark matter have not yet been found, so we can't claim that white holes don't exist. Well, let's move on to discuss the black holes. At first glance, everything seems to be perfectly simple with them. Any black hole can be described by only two characteristics, mass and rotation. But this is a mistake. There are wide, indirect varieties of black holes, and we'll discuss them later. But first, let's find out about the gold standard. It tells us that there are two categories of black holes in the universe, depending on their mass. The first category is stellar black holes, with masses from a couple to several tens of solar ones. The second is supermassive, with millions and tens of millions of solar masses. We have already found these two categories black holes and documentary evidence of their existence. The supermassive ones have been photographed. Everything is straightforward with them. This is the same black hole that arises in your mind at the mention of the topic. Usually, supermassive holes are located in the center of galaxies, where their monstrous gravity affects the motion of everything around them. The Event Horizon Telescope team recently published an epic zoom into the center of our galaxy. and the ESA telescope team supplemented it with the visualization of the star's rotation around black hole Sagittarius A. The motion was accelerated, and the video covers about 20 years of motion. Still, near the incredible gravity of a supermassive black hole, stars move at insane speed. Star S29, for example, approached the hole in May 2021 at a distance of only 90 times farther than Earth from the Sun, accelerating it to 3% light speed. That's about 9,000 kilometers per second. This figure is incredible, considering we're not talking about a tiny spacecraft, but a massive star. There's only one catch. We have no idea how supermassive black holes are created. There are 5 strong theories, but this is a topic for a separate video. In this one, we'll talk about the second category of black holes, stellar mass holes, which have a simpler origin. When a star burns out all its fuel, it starts to collapse. Depending on its mass, it turns into a diamond-like white dwarf or a neutron star, or a black hole. As a result, having the mass of several suns, this hole will not exceed a few kilometers in size. At the same time, it has the same gravity. It will immediately gobble up dust and gas entering the dangerous radius and grow in size. However, it will not grow to supermassive. With these 2 types of black holes, astrophysics existed for a long time. But later, scientists thought about the rather large spread of masses. It would make sense for intermediates between tiny and supermassive black holes, wouldn't it? So they called the hypothetical class of black holes, and they're still trying to look for it. Scientists are interested in holes weighing thousands or even hundreds of thousands of solar, which cannot be attributed to stellar ones, but are still far from being supermassive. They look for them mainly in dwarf galaxies. After all, if there are supermassive holes in the center of ordinary ones, then logically, there will be medium-sized holes in the center of tiny galaxies, right? So there are many potential candidates like NGC 1313X1, but so far, there is no clear confirmation of the existence of this black hole type, although there is 99% probability they exist. As a result, the number of black hole types has grown to 3. Following the same logic, scientists went further. Why shouldn't tiny black holes of the apple size exist? Or, on the other hand, super-duper mega-giga supermassive ones? Both are mathematically possible, or rather, it has become possible. For a long time, the mass limit of a supermassive black hole was a mass of 100 billion solar 1. The heaviest one humanity has found has a mass of 70 billion. But in February 2021, a team of scientists from Britain theorized that early in the life of the universe, mathematics allowed even heavier black holes, 1,000,000 times larger than the current limit, to exist. Officially, this category has been called incredibly large black holes, but there's still a lot of work to be done. The same can be claimed about another hypothetical category of black holes, called Planck mass black holes, or microholes. The size of such formations can be less than a proton. This is such a tiny black hole that its mass will have 10 to the minus 5th power of zeros after the decimal point. It will be equal to the mass of hypothetically largest elementary particle. They are called maximons, and scientists are interested in them because they can help solve the issue of dark matter. It's all very logical. After all, the main problem is that dark matter cannot be seen. What else can't be seen? Black holes. If the universe is saturated with such tiny black holes, many questions will fall into place. To explain this, theories of quantum gravity should be developed. However, the physics field is still very weak. But even here, the classification of black holes by mass does not end there. After all, there are still hypothetically black holes of planetary mass. There may be a mystery associated with them that keeps scientists awake. Surely you know about Planet X, the 9th planet of the solar system, which the brilliant astronomer Konstantin Batygin is searching for extensively. He is searching for it for a reason. Dwarf planets outside of Neptune behave as strangely as possible. First, they're further away than they're supposed to be. Secondly, the orbits of some of them hint at outside influence. Neptune itself was found similarly. It was first calculated mathematically by studying the orbital deviations of Uranus and other celestial bodies. Currently, the same thing is happening to the bodies behind Neptune. Mathematically, Batygin and his colleagues have long calculated the size and characteristics of Planet X so that the behavior of trans-Neptunian objects is logical. However, physically, we still cannot find Planet X, even though it is pretty healthy. This is where planetary mass black holes come into play. Astronomers Jacob Schultz and James Anwin proposed in 2019 to look not for Planet X, but for a black hole of the same mass in our solar system. Mathematically, this is possible. Moreover, it would explain why we can't find a large enough Planet X. However, on the other hand, there would be no contradiction in the behavior of trans-Neptunian bodies. It is just that their gravity would not be influenced by a large planet, but by a tiny black hole, with a mass of a few earthly ones. Here lies the main problem. With that mass, a hypothetical black hole would be the size of an apple, and finding it with a telescope is an almost impossible task. Gravitational lensing can help, but that's another story. The main thing is that theoretically, a black hole can safely fly in the solar system, and we may see exactly its effects. We're done with the sizes, so let's move on to other classifications. Besides mass, the main characteristic of a black hole is its spin. Almost everything that we see in the universe rotates around its axis. So why shouldn't black holes spin? Einstein's equations allow this, and observations of known holes confirm that they rotate. True, there is some catch. It is very challenging to calculate this rotation in kilometers per hour familiar to us, simply because a black hole, unlike a star on a planet, does not have a physical surface as such. The only way to evaluate a black hole rotation is to look at how matter behaves near it. Everything about it is very unclear and confusing, and there is still no reasonable classification and measurements. One of the black holes of stellar mass was managed to be calculated. GRS 1915-105, which is of the constellation Aquila, rotates at a speed of about 1,150 revolutions per second. Not bad, isn't it? The spin of this black hole is also calculated and equals almost unity. It is measured in fractions of the Planck constant, but this is a story for a separate video. In this video, we will continue to talk about the different kinds of black holes, including their physical characteristics and location. The first type of black hole in such a classification is stationary. Not literally, of course. Everything in space drifts and is in motion. But static black holes are more or less tied to one point. For example, Sagittarius A is located in the center of our galaxy and is not mainly in a hurry. The previously described GRS 1915-105 rotates as part of a binary system with a companion star. These holes are still hard to pinpoint, but at least they are a plus or minus in one place, and scientists know where to search. The situation with the second type, rogue black holes, is much worse. Imagine a huge star with a mass of several tons of solar masses collapsed after a supernova explosion. As we described earlier, collapsing into a single point, a tremendous amount of matter is compressed into a singularity, and a black hole appears. But this process is asymmetric, meaning the waves from a supernova explosion will not look like a perfectly flat sphere with a black hole in the middle. Our Sun, for example, is also not very smooth, and the mass in it is unevenly distributed. Consequently, when everything explodes and a black hole is born, there may be a little more matter on one side and a little less on the other. The gravitational waves from a supernova explosion will also be asymmetric. As a result, the created black hole may be ejected to one side. The phenomenon even has an official name, the birth kick. Having received such a punch, the black hole will travel through the galaxy. And considering that it is an object of huge mass, velocity, and momentum, it is almost unreal to stop such a nucleus. So these wandering black holes are doomed to roam the galaxy for millions and even billions of years. According to the most conservative estimates, only about 5 million such wandering black holes are in our Milky Way galaxy. The boldest calculations even claim 200 million. This type of black hole is widespread and at the same time is the most difficult to detect. Dozens of circumstantial evidence can detect a stationary black hole. Sagittarius A at the Milky Way's center strongly affects nearby stars' orbits. A black hole in a binary system interacts with its companion, devouring it and releasing radiation. Wandering holes, on the other hand, are real stealth fighters. They leave no indirect traces except one: gravitational lensing. Einstein's theory of relativity claims that massive objects bend space to such an extent that they even affect light. Over the last 100 years, this has been documented in dozens of different ways. For example, by using lensing, the Hubble telescope detected the most distant star and galaxy known to humanity. Gravitational lensing is a tricky thing, but all we need to know is that it can work like a magnifying glass. That is, light passing through the gravity of a massive body is amplified. The Hubble telescope amplifies its optics in a natural way. They also decided to look for rogue black holes in this way to look at the behavior of stars and changes in their appearance. In theory, if a black hole passes between the Earth and a distant star, we will feel the effect of lensing. The star for the observer will light up brighter than usual. Thus, this confirms the presence of an invisible object of enormous mass in between. The catch is that this is a rather tedious task. Some stars like to change their brightness, and it's not clear where to look. It took the Hubble telescope 6 years to find it, and another 5 to test the data. Finally, in February of this year, scientists announced that the black hole MOA 11191 was found by gravitational lensing. It was June 2, 2011, when a small star for as much as 270 days showed an unexplained increase in brightness. Such phenomena are registered annually, about 2,000. But this particular star was tested for a long 6 years. First, to be sure it was a case of gravitational lensing, the scientists note that in 2011, in front of this star passed an object with a mass of 7 suns, measuring about 45 kilometers in diameter. With a 90% probability, it is a black hole. In theory, it could also be a neutron star. But either way, the important thing is that the object isn't attached to anything. It's really wandering around the Milky Way on its own at an incredible speed of 45 kilometers per second. To understand the magnificence of the discovery, do not forget that we're talking about an event that occurs 5,000 light-years away. That is, by implication, scientists have spotted an object the diameter of a city at such an enormous distance. Just like seeing a hydrogen atom on the moon from Earth, it's a truly incredible achievement. Moreover, exciting is the thought that there are tens, maybe even hundreds of millions of such wandering black holes in our galaxy. It is almost unreal to notice them. They move quickly, and strangely, fans of the end of the world have not yet taken such a scenario of the Earth's death on notice. Well, and if this is not enough for you, in June 2021, members of the Royal Astronomical Society conducted simulations that announced that wandering could be a supermassive black hole. After all, galaxies too, in the formation process, eject asymmetric waves and periodically collide with each other. So black holes with masses of several millions of suns can drift through the expanse of space in proud solitude. Black holes can also be classified according to loneliness. It's common law in space that almost everything has a pair. The more we learn about the laws of the universe, the more we understand that our sun is an exception. More than half of the star systems we have found are binary, triple, or even quadruple. Single stars are not so common. The same law applies to everything, starting from the planets that most often have satellites and ending with galaxies that also have them. The Milky Way, for example, has several dozen satellite galaxies. Black holes are no exception to this law of the universe. They can also be binary. Moreover, this can happen either with stellar mass holes or supermassive black holes. In one of the recent videos on the channel, we even posted the sound of 2 black holes merging, which NASA received through sonification. The fusion process is truly amazing. On September 14, 2015, the LIGO gravitational wave detector detected a signal from merging 2 black holes with a mass of 36 and 29 solar masses. The power of the process at its peak was 200 solar masses per second, emitted in the form of radiation. This is 50 times the power of all the stars in the observable universe. It's good that this happened at a distance of 1 billion light-years from us, since the event occurred on a truly universal scale. However, the objects of the binary system do not necessarily merge. A black hole begins to eat matter only when it is dangerously close. Up to this point, she calmly interacts with the rest of the bodies without touching anyone. In addition, the companion is not always a black hole. It can be an ordinary star or a neutron one. When a black hole begins to absorb the matter of a neighboring star, it is better not to be too close. A couple of years ago, at the University of Southampton, they recorded fairly detailed data on the process of material absorption by a black hole. Based on this, scientists created a visualization of the process, which needed to be slowed down 10 times so that the human eye could at least somehow distinguish between flashes of jets of emitted matter. As you can see, black holes are cruel and harsh and beautiful at the same time, and as mathematicians, they periodically throw up almost impossible tasks. So, for example, in 2020, scientists recorded a black hole ejection of matter in the M87 galaxy. They studied two jets, which flew to a distance of 900 and 2,500 light-years, which is incredibly wild speed. But even more fun is that speed measurements showed that the first jet flew 6 times faster than the speed of light, and the second 2.5 times, which is impossible. Scientists had to rehack the data several times and consider the sources of optical illusions. As a result, it was revealed that the jets did not exceed the speed of light, but still, they moved at an actual speed of about 99% of the speed of light. The human brain can hardly even imagine such power. Therefore, this is why studying black holes is one of the most honorable fields of astrophysics. It is incredibly complex and challenging, and the calculations flash surreal numbers of velocities and masses. In addition, it is almost unrealistic to conduct thought experiments because our brains refuse to visualize singularities. Nevertheless, black holes may be the answer to all questions of humanity. Theoretically, they can explain the existence of dark matter, link quantum physics with classical physics, and even solve the problem of Planet X in the solar system. So let's wish the scientists good luck, hoping to get results soon. And if you liked our chit-chat, kindly put your like and comment. See you soon, friends.